Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm going to be talking to you about a novel form of machine learning. The novelty of this should become apparent, but it plays on the kind of fundamental property of computers that they can interpret their own programs, and there are programs which can interpret all other programs. So the central idea of a universal Turing machine. This is built into something called a meta-interpreter, which is a logical description of a universal Turing machine, and it's augmented in a way that it learns. Okay, so we're taking a general model of computation which learns by adding new facts in when it needs to. I'll be talking a bit about program induction, that is how to construct programs from examples, which is relevant to some ongoing work at Microsoft Redmond by Sumit Gulwani, but again, that should become apparent during the talk. So my starting point in the talk is about, if you go back to the 70s and 80s, the idea of using logic as a programming language was one which was advocated by Robert Kowalski. A bit later out of that, various different pieces of work, Shapiro, earlier work by Plotkin and so on, came together into an intensive study of something called inductive logic programming in around about 1991, which used the framework of logic programming as a basis for machine learning. So it used the representation of programs in the form of definite clause logic, which is a fragment of first-order logic, to formulate a machine learning approach to machine learning. In that early work, one of the characteristics that was slightly different at the time was this idea of predicate invention. That is, if you're trying to construct a program out of a given set of predicates, which are predefined, then in some cases you cannot complete the definition because you need certain auxiliary predicates. So if you imagine trying to learn reverse, you might want to have append invented, or if you didn't have it already. So that idea of predicate invention was characteristic of the early 1990s work. If in a retrospective of 20 years of inductive logic programming that I and some other authors wrote back in 2011, it was with some sadness that we recognized that both predicate invention and even the learning of recursive programs had been dropped along the way because these were too hard for the earlier mechanisms that were being used. They led to inefficient searches, and people preferred to concentrate on non-recursive logic programs for applications in knowledge discovery, largely. So in 2013, having written this, after having written this perspective, I thought it would be worth going back and seeing if there was a different way of looking at the problem. And out of that emerged the work that I'll be talking about of meta-interpretive learning. And now there's a paper on grammar learning in the literature, and ICHCAI, the main joint conference on AI, we published some work. I'll then show you what the basis of this idea was. So the starting example that I had in mind from my thesis in Edinburgh was actually the fact that other forms of machine learning had been applied since the 1950s onwards, looking at things like induction of finite state machines or finite acceptors from examples, and these had not avoided the issues which were related to both predicate invention and recursion. So to exemplify this, what I've shown here in the diagram is a simple finite state acceptor. Each circle here, it represents a state, Q0 and Q1. A double circle represents acceptance state, which shows that the string so far has been accepted in a language or in this target language. Here, if you get a 0 to begin with, you'll cycle around here. If you get a 1, you'll change state, and then you'll carry on with zeros and then come back with another 1. So this finite state acceptor accepts precisely the set of parity strings, those that have an even number of 1s, because as you start off here, you have seen no 1 so far. If you see 1, 1, then you go to the odd state. If you see another 1, you come back to the even state and cycle on zeros, etc. Now, it's clear that from work by Warren and Pereira, or Pereira's work, in fact, that we can easily formulate these kind of grammatical representations into a simple form of definite clause program and represent these in a language like Prolog. And even if you're not familiar with Prolog, you'll find that, in fact, this has got a very simple structure. So if you look here, the acceptor state is the one that goes from the empty string to the empty string. The arc here, the 0 arc here, goes from Q0 back to Q0. This is, if you like, a recursive loop. In this third case, you go from Q0 to Q1 if you get a 1 on the input, and so on. So each clause actually is associated with one particular arc or the acceptor state for the first one. And examples that you might get might be something like the empty string 0 or two ones or 101. These might be examples of the that you might be given in order to do the learning. So if we look at this, what we see is something that could not be learned by a standard inductive logic programming system, because it contains not only mutual recursion here in this loop, but also self-recursion, but also mutual recursion between these two. The predicate symbols, although you might be given, let's say, Q0 as a starter state, Q1 would certainly be something that wouldn't be given as part of the examples that you're given. You have to somehow invent that given these examples, because you don't see the Q1s in the examples. So there is both a predicate invention problem and a recursion problem in trying to learn this logic program. And so inductive logic programming systems typically cannot even learn regular grammars, which is extremely disappointing, given that part of the reason, the motivating reason for using logic programs is that they were very rich representations. And this is a simple fragment of first-order logic. Now, one thing that you can notice, though, if you look at these clauses, is that they have a lot of similarity. There's not a lot of variation between the clauses. So all of these 4 clauses here have a very similar pattern to them. The only thing that varies is, in this first place, the Q0, the constant here, which might be 0 and 1. The first thing might be Q0 or Q1. And over here, Q0 and Q1 vary. The rest of the structure of the clause stays the same. And so it seems natural that you might capture the regularities of these kind of clauses beforehand if you were aiming to learn DCGs. And in fact, that can be done just using these 2 patterns, of which occur, the second one occurs repeatedly, the first one occurs just once, which is the acceptor state. But you could have an acceptor that had multiple acceptor states. In fact, you will never see any other clause like, apart from ones that have this form, in a regular grammar, because this is another way of describing the Chomsky description of regular grammars. And if we look at these, we can also consider that they look a bit like clauses themselves. The one difference, though, is that we've got something odd here, that these variables will substitute not for constants in the language like 0 and 1, but for predicate symbols. Okay? So this is essentially some form of higher-order logic statement that would need to be given to the learner in order to be able to direct it to do this form of learning. So the idea came to me that what one needs to do is to somehow put these structures into a general purpose parser and use just those in order to direct the learning. And this is demonstrated in this slide. So the idea was to try and to direct the invention of new predicates using these two general clauses that I showed you before, implanted within a meta-interpreter. Now, you can think of this meta-interpreter as being a general purpose parser which has some specific types of rules in it. So for instance, here, the parser starts by calling this particular parse predicate, which contains, if you see, the first rule. And if that first rule matches, then it'll match because acceptor Q is true. And similarly here, the second one parses through here. You flattened out the structure of this clause and made it into meta-variables within the parser. If you think of the parser as being a kind of higher order predicate itself applied to these other predicates, you can do this within Prolog. But you would need these auxiliary predicates, acceptor and delta, to fill out the details of the grammar that you are actually trying to learn. So if we put these ground facts in, then we would parse exactly the parity language rather than some other language, because the acceptor, we're told here, is Q0, and this represents the transition table, if you like, of the finite state acceptor. So we're told here that delta takes Q0 state with a 0 to Q0 and Q01 to Q1 and so on. Now, suppose that we did not have these ground facts to begin with. We can use a mechanism from logic programming called abduction, in which if you do not have the facts that you need to prove, you simply assume the facts that are necessary in order to complete the proof. So by starting with an empty set of ground facts and using the same general purpose meta-interpreter, we can abduce the ground facts necessary to represent parity. And in fact, if you think about that, what we've done is we've turned the problem of inducing what was a first-order program, this one here, into the problem of abducing a zeroth-order program, a ground program, by abduction. Now, learning with respect to propositional logic or zeroth-order logic is a much simpler task than learning first-order logic, because this is a less expressive language. What's happened with this meta-interpreter is it's acted as a kind of projector. It's projected you from first-order representation onto a zeroth-order representation and allowed you to use abduction to carry out what would normally require induction. Hello.
I'm a little bit surprised. What you're saying is that, okay, so I might just by abduction infer all these ground facts, because that's what abduction does, is once we have a theorem and we're missing some assumptions to prove, so we can actually learn these assumptions by abduction. But that actually implies that you have a theorem in the first place.
And the theory in the first place is the interpreter, the meta-interpreter.
No, but so it feels like your theorem is that, okay, the language that is accepted has even number of ones.
No, not so. Because any regular language could be represented as a set of ground facts. I've just represented the parity language, if that's what you're saying, I'm assuming beforehand.
I thought that what you would like to learn, the ground facts, is a representation of automaton that gives you even number, no?
That is what you would like to learn, and your starting point is to have a meta-interpreter with no ground facts.
Yeah.
A set of ground facts that is assumed will then represent a particular language, in this case parity. After the ground facts are generated by abduction. As you go through the proof procedure, you abduce things as needed.
Yeah, but the proof procedure of a particular theorem, what would be the theorem?
This theory.
But so here it looks like...
Plus the input data.
You're saying you have a sort of a system for doing abduction for us as prolog programs. Is that the idea? So you've written
Not
Claude
yet.
programs.
You're jumping ahead a little bit. So what I'm trying to do is simply learn regular grammars. And so if I've given a string, a regular string like 101, and I parse it through this general purpose acceptor, if there's nothing there that says where the acceptors are or what the deltas are, it will introduce appropriate acceptors and deltas that parses that particular string. So with 101, it'll start off by saying, well, I need to be able to get a 1 in, and it needs to go from 0. So I'll introduce this atom. Okay, I haven't got the parity grammar yet. I've just got the first step in it, let's say. And now I need to go with a 0. I need something that goes from state 1, because we've now bound that. We introduce this one. And then we, again, have a 1 in it, and we end up with an acceptor. So we'll have generated part of the finite state acceptor. Given some more examples, we might be able to generate all of the transitions necessary to accept parity rather than some other language.
Starting material is a bunch of strings and their parities.
Yes, that's right. Those are the positive and negative examples. So
as many of those as you want or something?
Yes, you've got a set of positive examples, maybe some negative examples. So you must make sure that the negative examples fail in this procedure on any set of ground facts.
Okay, thank you.
Yeah, okay. So, and the completeness of abduction actually ensures that this procedure will learn any regular language. So an implementation of this learning for this learner for irregular grammars is actually pretty much what you're seeing here. So you have a learning program which is about 3 clauses long. Anybody can implement this in 5 minutes, and you will be able to learn the regular grammars. By extending this by 1 clause, an extra one which deals with the Chomsky normal form for the additional general case of context-free grammars, you have a learner for context-free grammars, for all context-free grammars. And although the learners for regular grammars are standard, and there have been many of them developed since the 1950s, you will not find a single general approach for context-free grammars that precedes the publication of this one in the Machine Learning Journal last year. Now, it's not efficient, but it does learn a class with very little effort in the programming, and the efficiency might be achieved by improving on that program. But it tells you that there's something interesting in this way of describing the bias over a particular language class. Now, you might decide that this is something that is really rather local to the learning of languages or learning of formal grammars. So in the next step that we took, we looked at another fragment of logic to see whether a similar thing could be achieved, i.e. very simple learning algorithms that achieve efficient learning by backtracking. Okay, so in this case, what we took is we decided to look at kinship problems. These have been studied by Hinton, by Quinlan. In ILP, these are a standard, and in logic programming, this is the kind of very first thing that you're taught how to do as a logic programmer. Over here, we can see a made-up family tree. Here are some standard kinship relationships, so parent XY if mother XY, grandparent if parent of parent, and so on, ancestor if ancestor of ancestor, or ancestor of parent. So we've got a set of clauses, or set of target clauses that we're trying to learn in these kinships. Now, interestingly, when you write these out, sorry.
When you learn grammar, what's the criterion for getting a good answer? I mean, on any finite set of training data, it's always regular. So, you know, your regular expression thing would have matched all your context-free examples as well, right? With a great big finite state.
So the standard techniques are those from computational learning theory, in which you assume a randomly sampled training set from the target theory, and then you test on an independent random sample from the same target theory. So we're not doing anything unusual in machine learning terms here. So if you look at the performance graphs, they're over predictive accuracy and just on the unseen data.
Right.
So it's something you can test given a large bunch of examples and
Oh,
see
yes,
how
of
well you
course.
did, rather than a theorem that you can say, given this input, this was.
Oh, no, this is machine learning. So you're, yes. Okay, so the question is, so this is a different class of logic programs, but do we have similar characteristics that we get repeated patterns again and again? And it doesn't take long to look through this set of descriptions to realize we're getting similar patterns appearing repeatedly. So we got one. How many of these have we got? We've got that parent of mother, parent of father. We've also got the special case of ancestor of parent, all fit this form. And this one here, we've got here. We've got another one down here, and great-grandparents. We've got 3 of those. In fact, these patterns appear quite frequently. But if we consider that the language that we're dealing with, characterized a bit like what we see here, has certain properties where we have binary predicates at most, and we have at most 2 atoms in the body of the clause, then the various different templates of this kind are not very numerous. We can actually enumerate those. These are 2, which are the only ones that appear in here. They appear repeatedly. In fact, they appear in other things. If we define cousin or we define sister or sibling, there are slight variants of these, but there are not too many. There may be 2, 3, 4 of those that appear repeatedly in standard kinship descriptions. So this little language I'm calling H22. H22 has 2 predicates, arity 2 maximal. You can have 1 or 2. You can have 1 or 2 atoms in the body. And by incorporating, again, these clauses in a similar meta-interpreter to the one I've just shown you, you can get, again, behavior in which you are inductively learning these rules by abducing ground facts, which are substitute for the capitalized variables here, the p's and the q's. The x's and y's always stay as they are, just as before. And you can also get predicate invention and recursive learning. So you need recursion to handle ancestor, in this case double recursion. But you can handle all of that if you have a large enough bag of predicate symbols that you can choose from. You can introduce predicate symbols that haven't been used before and build up the definitions as a side effect of simply parsing through your examples and testing them against the negative examples. So it's a fairly simple general approach. But again, you might argue, H22, well, what kind of a fragment of logic is that? But there is an answer to that. In 1977, this little fragment was demonstrated in one of the early logic programming conferences. If you add unary function symbols, you're able to implement a universal Turing machine within this very impoverished language. Okay, so just to explain what's going on here, imagine that you have a large, let's say, an infinite set of symbols, and the S's here and T's represent particular Turing tapes, okay? And if you like, the second argument represents the after case, and the first argument, the before case. This first rule tells you the rule of halting. So the UTM given S and S hits a halt statement on S, and that's it. It stops. The second case represents a cycle, so a recursive cycle. You go from S to T by first of all executing from S to S1, and then S1 to T, where execute fetches an instruction from S. It extracts the instruction F, and then applies F to S to give you T. Now, you might notice there's something a bit weird. This is not a proper logic program because we have here a higher order variable being applied to a pair. Now, surely you can't do that. Well, actually, this represents a little fragment of higher order logic, which is called which is a datalog fragment of higher order logic. And given that it's datalog, amazingly, it's decidable, right? So higher order logic, nobody uses higher order logic for anything that you would hope to execute efficiently, because there are terrible properties to do with unification, giving an infinite set of answers and so on. But for higher order data log, that's not true. Higher order data log's decidable. And so this procedure is if you only limit things to a finite set of symbols, gives a decidable procedure for which it approximates a universal Turing machine. Given an infinite set of symbols, of course, we all know the universal Turing machines have undecidable properties. You don't know whether they're going to halt or not. But interestingly, what we thought was a very limited little fragment of higher order logic is sufficient to implement a universal Turing machine or an approximation to one. We can also think of these templates, if you like, for clauses as being most general templates of a kind. We can view programs as being generated by printing versions of these in various different ones. And you'll see that the structure of these we've already seen. So if you see these clauses here, we've at least seen this one here in the middle already as an instance in what we've looked at. I call this the chain rule because it appears again and again. It has the same general rule as transitivity, or the same general form as a transitive relationship, but it's in a more general form. Okay, so we're going to have to, given that this is a very strong language, we're going to have to find strong ways of bounding it in order to guarantee termination of the learner, because the learner has to at least be able to terminate when it's constructing its solutions and testing them. So the implementation of a system called MetaGaldi has a control part. It hasn't just got the meta-interpreter I mentioned, but it also uses a bag of techniques, the first of which is called the ordered Herbrand base. This is an idea from Newton Bendix, 1970, who used it to develop confluent rewrite systems. Yaya, Fernandez, and Minker used this within deductive databases for datalog programs. The approach is very simple. If you think about trying to guarantee termination of recursion, imagine that your Herbrand base was ordered in such a way that whenever you applied a rule, a fact that was higher in the order had to be proved by facts that were lower in the order. And each of those, in turn, must be proved by facts that are lower in the order. Eventually, there's a base to that order, and the recursion terminates. So this simple approach requires simply any total order over the Herbrand base to guarantee termination of derivations. There are various different total orderings that have been looked at. The most obvious first one was looked at by Newton and Bendix, which is lexicographic. If you imagine the telephone order over the Herbrand base, then the lexicographic ordering will do. It's got certain problems, so it doesn't support mutual recursion. There are other orderings, and we use one called the interval ordering, which is based on the assumption of a total ordering over the constant set as well. And so with a total ordering over the constant set, we can treat any binary predicate as being an interval. If we then require that the predicates that are called have interval calls which are included within the called interval, then we can again guarantee termination because of inclusion of intervals. So if these are proper inclusions of intervals, we again produce guaranteed terminating behaviors. And the various orderings, interestingly enough, are associated with various different time complexity classes for the learned objects, which is, again, an interesting topic that needs to be further explored. But I've already seen these in the experiment. So the second idea is that of episodes. And the idea here is analogous to human learning, to episodic logic, but the idea is that you carry out a sequence of tasks in which a program is built up as a series of definitions, one on top of another. Now, in the case that you're trying to learn a very large program, this produces a great increase in the efficiency because instead of searching the cross product of all of the hypothesis spaces for a large number of predicate symbols, in each episode you concentrate on getting one predicate definition correct before moving on to the next one, which is higher up in the order. Remember, our predicate symbols have an order. So building one predicate definition on another ends up producing the summation of the size of the individual hypothesis space rather than their product, which is a big gain. The clause hypothesis classes are then tested progressively. What that means is that we test a small number of clauses for each definition, and then consider a larger number of clauses. So we're looking at larger and larger spaces. This is, if you like, a very similar strategy to what's called iterative deepening in theorem proving. And in fact, because our meta-interpreter is a little theorem prover, we can view this as a way of enlarging the language by iterative deepening. So we're looking at small sub-definitions with one clause, two clauses, etc. And we don't move on to the next class until we've found we cannot find the solution in the class so far. Now, it's very easy to show that this guarantees that the solution will have the minimal number of clauses. The proof of that is obvious, because if there were a smaller one, you would have found it in an earlier class. By adding a further notion of log bounding, that is, we only look at classes up to size log n when we have n examples, we can actually get a pack sample complexity result. This is Les Valiant's probably approximately correct learning framework, where we can guarantee polynomial time construction from a polynomial number of examples by considering that the hypotheses are much smaller than the number of examples. Now, this is quite a strong constraint, but it's a constraint that guarantees high accuracy in every one of the definitions. And high accuracy actually helps if you're doing these episode learning tasks. The implementation of all of this is less than 100 lines long, and it's available to anyone who wants to try it out. We published this at ICHCAI, this algorithm, last year. Okay, so that's a lot about the implementation. So what use is this? The first interesting task that we came across was something presented at the Inductive Logic Programming conference in 2012 by Claude Samet, in which he had been using a Microsoft Kinect 3D camera to try to build a definition of a staircase for use within something called the RoboCup Rescue Robot Competition, which is an annual competition for trying to build robots that help firemen in burning buildings. So the fireman wants to be able to recognize a staircase. And when Samet looked at this problem, he took the point clusters from the Kinect camera. He then clustered these into planes, and he used an Aleph ILP system to learn a definition. When I asked him afterwards, was this definition recursive, he said no, and kindly offered to let me try this data out with our newly devised meta-interpretive learner. I hoped that we would be able to learn a recursive definition, maybe with some predicate invention from this rather messy data. It took about a day to figure out how to put it into the right form. And this is what popped out. Okay, so the pairs here represent so X represent the intersection of two planes, and Y similarly. So a staircase is defined by two lines. So the intersection of planes are lines. If we're given a line at the top of the staircase and a line at the bottom of the staircase, we get this tight little recursive definition, which goes staircase xy if A xz and stair zy, and so on. And A is defined in this way here. This is an invented predicate, so it's introduced automatically from the symbol set. Anybody want to hazard a name for A? Step. So the interesting thing is that this is instantly recognizable as a recursive general purpose definition of what a staircase is. It's a pattern which repeats, consisting of steps. I don't think you'll find many forms of machine learning that can actually get this from a single image. This came from a single image built in 0.08 seconds on a laptop. And it's using essentially the same set of meta rules that I showed you for the case of family relations. It's finding this is a bit like an ancestor where you're inventing this particular thing here to describe step. Sorry.
Go beyond your H22 fragment?
No.
It's within, right?
It's within. We've got arity 2 predicates everywhere, at most 2 atoms in the body.
How many symbols, predicate symbols, were in this image, or how you call it?
Originally, we had vertical and horizontal these were primitives, if you like, which are associated with a test on one of Samet's planes that is roughly up and down, and horizontal roughly horizontal. And the examples, the set of examples were all defined as stair pairs, so we've given them as stair line 1 to line 2.
Basically, the A and stair symbols.
Yes.
Along the way. Oh, thank you.
So this is pretty robust. You can take, there are a number of these lines, and you can take from a single staircase, a single image, you can take groups of pairs from within there in roughly any way you like, and it'll come up with this definition. And interestingly, you can see the computation path that the learner took, right? When it came first to the first pair, it tried to say, oh, well, could I just apply something like this first rule? Well, that would be staircase xy of staircase xy. So that doesn't work. So then I'll just introduce something or another. I'll just leave that for the moment and then go down into that. And what do I find with the first part? Well, it's vertical. You could have said, well, why didn't it test vertical here? Because it's got a boundary of 2 clauses in the body. It wouldn't have been able to fit everything in. So with an extra predicate, it can go vertical, horizontal, and now it sees a stair problem. It recurses back to here. We'll keep recursing down it until it hits the bottom of the staircase, and then it'll say, oh, that's another one of those. It's another step. Okay? So the construction path for this is the execution path of the solution, which means that the solution does not need to be tested again on the examples because it's true by construction. It's been proved by the meta-interpreter to work already.
So basically here, so you go essentially sort of you add backwards the steps. So if you let your system run for a little bit longer, is it going to come up with different definitions?
Yes, in general, it'll find a set of solutions. In this case, I'm not sure, but in Prolog, this is just a Prolog program. You run the meta-interpreter. If you want another, it'll give you the first solution. If you want another solution, it'll give you another one.
It was not the one that you picked because it looked nice.
No, it's the first solution. It's the first solution. Part of my surprise is that it was so easy. Once the data was there, it just came out immediately. It wasn't, and I think there are.
Is it robust? I mean, on other images, I mean, you showed one picture.
I should still test that. I haven't tested that, but I'm pretty sure it's. Oh, actually, no. We did some robustness tests. This is in the grammar. This is in the machine learning journal paper. We did robustness tests on the remainder of the images, and it got very close to 100%. There was some noise in the data, so it didn't get absolutely 100%. Okay. Okay, so interesting. So this is an example of what you might call, what Josh Tenenbaum and MIT calls one-shot learning. That is learning from a single instance. And you'll see this again. Okay, so there are some other tasks that we looked at. So learning a robot strategy can be done in this fashion also. And here is a program, again, in the Ichkai paper, where we learned from various different, we given actions and monadics map onto binary and, actions and fluence, that's tests and actions for this planning problem are given as dyadic and monadic predicates. And this definition is learned for building sets of bricks. It's a recursive definition. It introduces extra predicates here, F1, A2, and so on. If you've only given it positive examples, it builds a simple recursive build structure where it fetches and puts things on top of. If you give it negative examples from piles of bricks that have fallen down, then it will build you these additional parts which test the robustness of the solution. I'm running out of time, so I won't go into this in too much more detail, but these are the kinds of examples that were given as pairs, before and after pairs, where you have a pile of bricks and the after one. And these before and after states of the world are represented by variables x and y. Okay, so F1 is just a test on a state. This is the learning performance on unseen data. So as we increase the number of randomly chosen examples for the wall building from 0 to 70, the accuracy goes quite rapidly up to near 100%. And the learning time increases roughly linearly because we're using an interval constraint. And these are randomly chosen training sets and tested on the remaining test sets. Okay, so we can learn little robot strategies. In fact, these are non-deterministic strategies, but they become more deterministic as you provide more examples. Okay, so I mentioned Sumit Gulwani at the beginning, so a number of you may be aware of his work, but I only became aware of this in December. And the FlashFill program, for those of you who are not aware of it, is an amazing program which allows you to take an Excel spreadsheet, given a certain column of values. The user can then specify a particular transformation, string transformation that they want. Okay, so in this case, the user types in Brent Harold, and the computer is then supposed to work out what the transformation is as a program. And the reason it's called FlashFill is that in a flash, it fills the remainder of the column with the transformations based on a program that's been built out of what is called a domain-specific language, a restricted language. It works over a class of problems that have been entered by hundreds of thousands of entries given by users and is part of the 2013 Excel release. Okay, so this is a pretty solid piece of work of using inductive programming. And it's one of the most prominent examples, or probably the most prominent examples in the world now, of efficient and effective inductive programming from a small number of examples. By small, in this case, we mean on average, according to his tests, 1.2, after a lot of frequency analysis of the data and so on, and careful tweaks at the Redmond group. This works really, really well. Okay, so having seen this, I was quite inspired to the idea of trying to apply meta-interpretive learning to functional programs to see if one could get some similar effect to this, but maybe go a little bit beyond what this brilliant work by Sumit Gulwani has achieved. So this is a Popple paper in 2012 that was also became a highlight paper in the communications of the ACM in the same year. So this is very recent work. But one thing that it fails to do in my regards at the moment is, first of all, to show you the underlying program that's been built, which is slightly complex from having read the papers. And secondly, to improve learning. So you're given a domain-specific language that has some specific actions that can be applied. How could we build a system that would get better at this task the more often it did it? Okay, so I've been working during January with the Brain and Cognitive Science group at MIT, and we've come up with a first cut at this. We're partway through a set of 30 examples which are like those given by Sumit. And here's a particularly interesting interaction. So the same example, is given here, Brent Harold. We're assuming that we're using that same dyadic MetaGaldi system, but with a test that the relations that are learned are functional. That is, for any input, there must be precisely one output. So for every A, there must be precisely one B for the solution to be acceptable. So with that constraint, we get this program built for here. And I can actually show you what this program is doing. So this is episode 4, is this particular problem. It breaks the problem into 2 parts, EP41, 42. EP41 calls to EP43, and similarly EP42 goes to EP43. So there's obviously something going on in EP43. This does make uppercase and copy word. That's building that word Brent. It's taking the input and it's making it uppercase to capital B, and then it's copying the rest of the word, R-E-N-T. And if you see what happens after that, here you skip you skip 1 here, that skips over the dot, and then you do it again. You do it with Harold, and that's the program that does it, right? So this program is built using the same approach, meta-interpretive approach. It takes 9 seconds to build that. Okay, that's much, much slower than flash fill, right? So what's curious, though, is that we've got this reuse of the invented predicate, which happens partly because we're minimizing the program that's built. The space, by the way, that's being searched to find this is of size around about 10 to the 15. But very little of that space is explored because we're only looking at things that are consistent. Okay, so what happens if we look at several episodes? Well, in fact, episode 2 out of the set of 30 problems is this one. Take James and capitalize it to James with a full stop at the end. Now that problem produces this solution. So it says, okay, make uppercase and word, copy word, and then write a dot at the end. But you notice that this make uppercase copy word, we've seen that before. It's a sub-procedure that has been invented, and then it can be reused. So the solution now for EP4, this problem, is 1 clause shorter than before, because we are reusing this EP021 twice over here, which shortens the program. A shorter program is found much faster. Look, the time here is 3 seconds to do 2 problems, 2 episode learning problems, rather than 9 seconds to do 1, right? So we're getting a big speed up, well, relatively big, 3. In fact, there are other pairs of problems in this set that we've looked at where the speed up is up to 40 times faster because of this kind of reduction, because you're finding useful sub-predicates that can be used again, or subroutines or sub-functions that can be used again. So I would claim that this is actually a rather nice example of Hoare's law of large programs, that every large program contains small subprograms within it, and more than that, that these can then be reused and produce more efficient programming or learning in this case. So I'm having to watch the time now, because I'm running a bit short. So I've got 5 minutes left. The issue struck us at one point about how do you turn this into a probabilistic reasoner. And it turns out that we can take a meta-interpretive approach like this. We can view the space, the hypothesis space, as being the set of prologue derivations that can be produced. And the set of abductions from those are sets of ground facts, which can be treated as programs. So for learning finite state acceptors, here's part of the derivation space. So here's one loop being introduced, and that's extended with a 1, and so on. Now, if we take this derivation graph, or refinement graph as it's called in the inductive logic programming literature, and label the individual outgoing arcs of the tree with probabilities that are chosen uniformly at each level, so if there are 10, a branch out of 10 here, each one of these will be 0.1, then we define something which is essentially a Bayesian sampling distribution. And in this case, it would be for the finite state acceptors or for programs in the more general case. The property is that each one of the leaves at the end of the tree is consistent with all of the examples. And as you get more examples coming in, positive and negative examples, the derivation space grows and shrinks according to parts that have been pruned out by the being consistent with the examples. So you can think of this as an updatable Bayesian posterior probability distribution. It's an efficient way of updating the posterior distribution over a structured distribution. So we can set up, I don't want to go into detail with this, but you can set up all of the standard things, the prior, the likelihood, posterior, and so on, in terms of this graph, and compute probabilities of hypotheses given evidence in the standard way as the product of likelihood and prior with a normalizing constant. So skipping forward because of time, one nice property that we found is that you can efficiently sample from this derivation space by choosing target probabilities. So one of the difficulties to begin with is when sampling from such a tree that's built on a stochastic logic program for the Meta-Interpreter, you get lots of repeat solutions if you do the simplest method of sampling with replacement. However, you can produce a sampling without replacement approach by simply choosing a target, let's say 0.5, and you now know that the interval, which represents the sum of the probabilities up to a particular point, a particular hypothesis, that cumulative probability, if you sum that up under the first branch, it'll sum to 1/3, under the second branch to 1/3, and under the third branch to 1/3 because of the uniformity assumption. So if we're looking for the probability, the hypothesis associated with 0.5, we know it's down the second arc. And this holds for every level. Okay? So we can walk from the root of this derivation tree to a particular hypothesis associated with a target probability. And we can then use that to do sampling without replacement. So if we choose the series 0.1, 0.2, 0.3, we can systematically choose distinct hypotheses which are maximally spaced across the space. They'll each be different, so we're doing sampling without replacement in a regular fashion. And this is very efficient because each sample just takes log n times to get to the consistent hypothesis when walking through the derivation space. Okay, so we've used this. We use this in order to build a Bayesian predictor, so an approximated Bayesian predictor, where we build, in this case, regular grammars, in this case, family definitions. We've compared Bayes prediction with sample sizes of 1,750 against a map solution. This is a maximal posterior probability solution. We find, as theory predicts, that the Bayes predictor does better. Bayes prediction is a theoretical, largely a theoretical thing if you look at the machine learning literature. Here we're doing it for real. We're sampling from the space and we're doing the predictions. And we're finding that it's, at least in the case when you have small numbers of examples, the differences between the Bayes predictor and the map prediction are significant. If you're going to learn from a small sample, use a Bayes predictor. That's the outcome from this initial experimentation. A second idea was that of taking these solutions, which are each consistent hypotheses from across the space, and superimposing them. So this is a deterministic regular automaton here, H1, H2, H4, sampled across the space. In this case, these are 4 that are consistent with these 2 examples. So if you had only 2 examples with a maximum of 2 states, then these are the 4 consistent hypotheses. If you superimpose those, you get a kind of automaton with probabilities associated with the individual arc. So a 0 goes from Q0 to Q1 with probability 0.5, and back here with probability 0.5, but a 1 goes back and forwards here with probability 1. These probabilities are simply formed by summing up the appropriate probabilities over here. So this one is formed by seeing where the zeros are in that correspond to that arc, and 0.25 plus 0.25 is that 0.5 there. So we can build a probabilistic logic program in this fashion, and you might say, well, what kind of probabilistic logic program is this? And in fact, by looking at by looking at the construction, it turns out that this is a standard form of what's called problog. This is a form of probabilistic logic program developed in Leuven. Their method of estimating these labels is using expectation maximization, which is a standard statistical approach. Here, what we're doing, by taking samples, you can simply sum up those that have the appropriate arcs, and you can sum up the frequency with which they occur, and converge on the same solution. This convergence is guaranteed by the central limit theorem to get accurate, sufficiently accurate labels here. Expectation maximization actually is not. And in tests, these problog programs are being learned more efficiently, we've found, using this form of estimation than the original form. Okay, conclusions. So what I've talked to you about is a new form of machine learning called Meta-Interpretive Learning, based on ground abduction. It carries out two tasks that were previously thought very hard within the inductive logic programming community. That is efficient predicate invention and learning recursion. The definitions are simple, they're compact, they produce nice readable logic programs. We've managed to look at tasks that go beyond the simple bunch of classification-based learning tasks that you see in many forms of machine learning. We're able to approach tasks like hypothesis-driven visual pattern recognition in the staircase example. It's just one example. It's not demonstrated on very much. But all of this work has been done within the last year and a half. Okay? So robot strategy learning, we've shown how you can do that to build an effective strategy which improves with small numbers of examples. String transformation, we've started looking at this as a form of bias change related to the Gulwani problems. We're finding things that I think are quite interesting to do with how this approach can demonstrate problem decomposition and automatic introduction of subprograms in minimal program construction, in a minimal program construction approach. And we're also showing that we can build a Bayesian version of this meta-interpretive learning. The reason that the progress has been fast here is because the learning algorithm and variants of it can be written in a few lines of prologue. We're able to build these meta-interpreters and test them within days, and that has led to very rapid progress in developing this approach. So, if I leave you, that's the bibliography of papers on this so far. Gulwani's is the last paper down here, which is in Popple.
Great. Time for questions from Andre.
So I'm curious, so there's this search space, for example, for these H22 clauses. And it looks like one of the pruning techniques is you do this Knut-Bendix completion.
Yeah.
So do you do anything else beyond that?
I described the other things that we do in the implementation. Sorry, here. That's one thing. The second thing is episodes, so building one solution on top of another. You saw that in the Gulwani episodes 2 and 4. Here, so searching from small numbers of clauses in the solution to larger number of clauses. The log bounding, that is, put a bound onto the maximum size of program that you're going to consider. So those are the main three, I suppose, four things that are done in order to produce efficiency over and above. So this is the control strategy, which is an extra logic program over and above the basic meta-interpreter. The very earliest forms of meta-interpreter looked like the ones I showed you. The form that I've got now is a general purpose meta interpreter which you just load up with meta rules of the kind that I showed you. So you can reformulate using a general meta interpreter. You can just choose your meta rules. And there's a further approach that we're looking at the moment where you step up classes of program classes by adding, start off with a small number of meta rules and then add in progressively more in order to search larger and larger spaces. You'll stop whenever you succeed, right? Because what you're doing is trying to find the first solution unless you're searching stochastically. Hi, Thor.
Yeah, super interesting work. I was wondering, when you do these superimposed logic programs, is there anything stopping you from weighing the superimposition or the averaging really of the probabilities by some kind of likelihood term that would be driven by the number of errors that a given hypothesis makes on the training data? You could imagine including in your space hypotheses that maybe get one of the examples wrong and give them less weight, but there would presumably be more of them to make up for that. And you could deal with noisy data in that way.
Yeah, we haven't looked at that. What we have taken a look at is using the Bayes predictor to try to detect noisy data. Okay, so if in the situation in which you use the Bayes predictor, you get a probability associated with a prediction. Okay, even if you're using deterministic solutions like deterministic grammars. Now, in the case that that probability is close to 1, it's predicting that it's a positive example. If its actual label is 0, and you've got a number very close to 1, then it looks like noise, or the other way around. If it's predicting a Bayes prediction very close to 0 with a positive label on it, looks like noise. Okay, so what we're looking at in this work is, which I didn't describe here, is using the Bayes predictor in order to do things like noise detection and also for active learning. So for identifying instances which you would like to get more information on. And those ones tend to be ones which have probability close to 0.5.
Right, that bisect the version.
Which bisect the version, exactly, yeah. Hello.
Hi, somewhat related question here. Can you say a little bit about, it seems like there's a correspondence problem here. How do I know that Q1 in one of these figures is the same as Q1 in one of the other figures?
You're right about that. So we're just doing something simplistic. So we had here a bag of symbols, and we're just generating all of the solutions and then matching up on the same symbol in each case, right? So I agree. I don't have a particular answer to your question, but it's an interesting question.
So what happens if the training data is a little wrong? The user just...
Well, that's the noise question. So if we've got wrong classifications on the examples, then I'm suggesting we might try to detect that using Bayesian predictions. Okay, and then eliminate it. Well, we haven't tested that approach, but that may be an approach to. We haven't dealt with noise up till now.
FlashFill would get that wrong. If you make a mistake in the training data, they will not recover.
Yeah, FlashFill's the setting of FlashFill makes that particularly hard, I think, the noise problem, because the noise could be anywhere. Normally, with like binary prediction, the noise just changes a 0 to a 1. In the case of FlashFill, it's quite a complex output, and a single piece of noise might just be an unusual thing that you're being asked to do, right? That's not present in the other example. So it's tricky. I'm not sure how to handle that at the moment.
If there's no more questions, let's thank Stephen for a fascinating talk.
Thank you.